Have you ever wondered how the ancient Egyptians built the pyramids with such precision? These colossal structures, standing tall and proud, are not just architectural marvels but also mathematical wonders. Their precise measurements, perfectly aligned angles, and the sheer symmetry are enough to leave anyone awestruck. And yet, they were built thousands of years ago, long before the advent of modern tools and technology. But how did the ancient Egyptians achieve such precision and accuracy? The secret lies in the realm of mathematics. Yes, mathematics, the universal language, played a significant role in the construction of these architectural wonders. From the very dimensions of the pyramids to the alignment with celestial bodies, every aspect of their design and construction involved meticulous mathematical calculations. These calculations were not just about constructing a structure, they were about creating a monument that would stand the test of time, a symbol of human achievement and ingenuity. So let's unravel the mathematical secrets behind these ancient structures. First off, let's dig into the dimensions of the pyramids. The measurements, angles, and ratios used in pyramid construction are nothing short of extraordinary. The precision required to achieve the pyramid's geometric shape is a testament to the ancient Egyptians' mathematical prowess. The base of the pyramid, which is a perfect square, is crafted with such precision that the difference between the longest and shortest sides is often less than a few centimeters. The angles of the pyramid, measured from the apex to the base, are meticulously calculated to ensure the sides slope uniformly. The ratios used in pyramid construction also bear mention. Specifically, the ratio of the pyramid's height to half the length of the base is remarkably consistent across many pyramids, often approximating the golden ratio. Such precision in construction is no small feat, especially considering the tools and technology available at the time. These exact dimensions suggest a sophisticated understanding of geometry. Now, onto the intriguing base-to-height ratios found in many pyramids. The precise design of Egyptian pyramids reveals a consistent pattern in the ratios of their bases to their heights. This isn't just a random occurrence but a calculated design choice. One of the most well-known ratios is the golden ratio, which is approximately 1 to 1.618. This ratio, often symbolized by the Greek letter phi, has been found in many aspects of nature and art, and is believed to contribute to what humans perceive as aesthetically pleasing. In the context of pyramid construction, this ratio suggests a meticulous attention to geometric perfection. The base-to-height ratio wasn't just about aesthetics though, it also had practical implications, influencing the stability of the structure and the amount of materials required for construction. These consistent ratios are no mere coincidence but the result of careful calculations. How much stone did it take to build a pyramid? Let's find out. To answer this question, we need to delve into the world of volume calculations. The volume of a pyramid is calculated by multiplying the area of the base by the height and then dividing by 3. So, imagine the base of a pyramid as a square, each side measuring, let's say, 500 feet. The area of the base would be 500 feet times 500 feet, which equals 250,000 square feet. Now, if the height of the pyramid is 480 feet, we multiply the base area by the height, giving us 120 million cubic feet. But remember, we need to divide this by 3, as per the formula. Our final volume calculation then would be 40 million cubic feet. That's a lot of stone. So with a bit of math, we can estimate the sheer scale of these monumental constructions. Trigonometry is not just a high school subject, it's a pyramid builder's tool. Now when we think about the Great Pyramids of Egypt, what comes to mind? Besides their grandeur and mystery, it's their precise angles and slopes. And that's where trigonometry comes into play. Trigonometry, the branch of mathematics that deals with the relationships between the sides and angles of triangles, was instrumental in achieving such precision. The ancient Egyptians likely used rudimentary forms of trigonometric functions like sine, cosine, and tangent to determine the angles and slopes in pyramid construction. Imagine standing at the base of a pyramid, looking up at the peak. The angle of your gaze, the height of the pyramid, and the distance you are from the base form a right triangle. With the help of trigonometry, the Egyptians could have calculated this angle, ensuring the pyramid rose at the correct slope from the base to the peak. These trigonometric principles helped the Egyptians construct these architectural wonders. But how did the ancient Egyptians measure and align these massive structures? That's a question that has intrigued mathematicians and archaeologists for centuries. The answer lies in the tools and techniques that these ancient builders used, which were simple in design but effective in application. One of the basic tools was the plumb bob. A plumb bob is a weighted object, typically conical in shape, that's hung from a string. When it's allowed to swing freely, it aligns itself with the Earth's gravitational pull, providing a vertical reference line. It's a tool that's still used today in construction and surveying to ensure that structures are perfectly upright. Another essential tool was the cubit rod. This was a standard measuring stick, roughly equivalent to the length of a forearm. It was subdivided into 7 palms, with each palm further divided into 4 fingers. The cubit rod was used to measure lengths and distances with surprising accuracy. The consistency of these measures across different pyramid sites shows the precision achieved using this simple tool. Sighting instruments were also crucial for aligning the pyramids. These were likely simple devices, perhaps a straight edge or a leveled string, which allowed the builders to sight along a straight line and align the pyramid sides with the cardinal directions. The remarkable alignment of the pyramids with true north suggests the use of stellar observations, possibly using sighting instruments to track the motion of stars. While these tools may seem rudimentary by today's standards, it's important to remember the sheer scale of the pyramids. These were structures that reached up to 481 feet in height, built with millions of blocks of stone. The fact that they were constructed with such precision using these basic tools is a testament to the ingenuity and mathematical understanding of the ancient Egyptians. With these simple yet effective tools, the Egyptians achieved astonishing accuracy in their construction. The pyramids stand as enduring monuments, not just to the pharaohs they were built for, but also to the mathematical and engineering skills of the people who built them. Did you know that the pyramids align with celestial bodies? This intriguing aspect of pyramid construction is a testament to the ancient Egyptians' understanding of the cosmos. Let's delve deeper into how they achieved this. The alignment of the pyramids with celestial bodies, such as the North Star, is no mere coincidence. The Great Pyramid of Giza, for instance, is aligned with remarkable precision to the cardinal directions: north, south, east, and west. This suggests that the builders employed sophisticated mathematical calculations in their design. But how exactly did they do this? One theory suggests that the Egyptians used a circumpolar star to establish the north-south axis. By tracking this star's movement across the night sky, they could accurately align their monumental structures. Furthermore, the alignment of certain pyramid complexes with the sun's path during solstices and equinoxes hints at a connection between pyramid design and the solar year. The precise alignment of these pyramids confirms the Egyptians' advanced knowledge of astronomy and mathematics. So, what do these mathematical secrets tell us about the ancient Egyptians? Firstly, we've seen how the pyramid dimensions, with their precise measurements, angles, and ratios, demonstrate a sophisticated understanding of geometry. The Egyptians didn't just pile stones haphazardly, they designed and built with a keen eye for precision and symmetry. We've also delved into the intriguing base-to-height ratios found in many pyramids. The consistent presence of the golden ratio, a mathematical principle we still use and admire today, suggests a level of mathematical knowledge far beyond simple counting and measuring. Our exploration of volume calculations showed us that the Egyptians had a practical understanding of mathematics. They could estimate the volumes of their pyramids, a skill essential for planning and managing the vast resources and labor required for such monumental constructions. Trigonometry, a branch of mathematics that many of us find intimidating today, was also seemingly within the grasp of these ancient builders. The use of sine, cosine, and tangent in pyramid construction is evidence of this. The Egyptians' surveying and measurement tools were rudimentary by today's standards, yet they achieved an accuracy that we would struggle to match even with our advanced technology. This tells us of their ingenuity and adaptability, their ability to make the most of the tools at their disposal. We've also seen how the alignment of the pyramids with celestial bodies and cardinal directions may have involved complex mathematical calculations. This suggests that, for the Egyptians, mathematics was not just a practical tool, but also a means of connecting with the cosmos. Finally, we looked at the potential mathematical and symbolic meanings associated with the layout and proportions of the pyramids. This tells us that the Egyptians saw mathematics as more than just numbers. They saw it as a language, a way of expressing ideas and beliefs. The pyramids stand as an enduring testament to the mathematical prowess of the ancient Egyptians, reminding us that mathematics is indeed a universal language.